Section 17.4 Conductors, Insulators, and how we can charge different materials. Each atom by itself is electrically neutral. So it means that there is equal number of protons and electrons. For example, copper. But when these atoms come together to form a piece of metal, some of the electrons are freed. These conduction electrons can move freely through the metal. Logically, those electrons that are free to move through the conductor are called conduction electrons. They leave behind positively charged ion cores that bound and cannot move. Another important point, that a piece of metal can accept extra electrons or release some of its conduction electrons. So entire object can acquire a net positive or net negative charge. Insulators are materials where electrons are not able to move freely, again, rather logically. For example, plastic, amber, glass, quartz. Electrons cannot escape from these ions. They're bound to stay in. There are no conduction electrons available to carry charge through the solid. If extra electrons are placed on insulator, they tend to stay in the place where they initially placed. Liquids and gases behave like conductors. Even though the total charge is zero and the sample is neutral, a few molecules always dissociate into free ions. That means one electron is lost. Those ions can carry charge from place to place exactly like conduction electrons do. In this picture, this is water, but gases behave similarly in the same way. So what's happening when we're charging an insulator? For example, we can take a plastic rod and wrap it with a bunny fur. This way we would transfer extra electrons to the plastic rod and it will become negatively charged. Electrons that we placed on a rod, they will tend to stay exactly where they've been placed. However, they will attract positively charged ions from the air that always floating around, and insulator will eventually be neutralized. What happens if we add excess charge on the metal? Remember, electrons can move easily through metal. Because of Coulomb's law and electrical forces, all extra charge will end up on the surface of the metal. It doesn't matter, positive extra charge or negative charge is going to be always residing on the surface of the metal. How much charge will go on top, on the surface? All extra, so that inside conductor electric field is zero. This is actually extremely important fact. Electric field inside conductor is always zero, and all the extra charge on the metal is always on the surface. This is true only for conductors, not true for insulators. Just to review and repeat, for metal in equilibrium, any excess electrons must be at the surface. The electric field is zero inside a metal in equilibrium. Equilibrium reached pretty fast, so you can assume that pretty much right away when you add electrons on a metal, it's going to all go on the surface and everything inside is going to be electrically neutral. If we add positive net charge, that means that electrons were removed from the metal. So this deficit of electrons will be also at the surface. So the surface will have a net positive charge. How we can charge an object? Simple way, how it was done in Greece and how we can do it right now, is by rubbing insulator. When you have an amber rod and you're using fur, like in this picture, you're transferring electrons from a fur to an amber, and amber becomes negatively charged. If you're using a glass rod and silk, then electrons from the glass are going to be jumping on the silk, and glass will stay and will have only positive charge left. Also, just to review, that the silk is going to have negative charge, and the fur is going to end up being positively charged. What is polarization? This is an important electrical phenomena. Let's start with the rod and paper that both electrically neutral. We will then charge the rod by rubbing with fur, which place negative charge electrons on the rod. We would bring the rod next to the paper, like in this picture. So what's happening to electrons in the paper? Electrons in the paper that are close to the rod are going to feel the force that pushes it away from the rod. So they are going to end up on this side of the paper. They run away. They don't want to be next to the rod. So here we're going to be left with positively charged particles. And paper is still electrically neutral, but it says to be polarized because there is separation of charges. This is just a summary, what I just told you. The paper is still electrically neutral, the same amount of electrons as protons. However, the charges are moved and negative side of the paper is repelled. The positive side of the paper is closer to the rod, so it will experience a greater electric force. So the net effect is that the positive charge of the paper is attracted to the negative rod. That's why the piece of paper can stick to the rod. There will be an electric force of an object even when an object is electrically neutral, provided the object is polarized. This is a very cute example, and I call it magic. You can play it at home, especially if you have little kids, like brothers, sisters. So take a balloon, blow it up, rub it with a fur. If you have a cat or a dog, rub it on your cat or dog. It's a very good fur to be rubbed on. So you can also rub on your hair if you don't want to mess it up. What will happen then by rubbing? You will transfer electrons to the balloon, and the balloon will become negatively charged. So then if you would place balloon near to the water, water will become polarized, and you would experience this deep in the water. Another one that I like to do, if you rub the balloon using your cat or dog and put it next to the wall, balloon will stick to the wall and will stay quite a bit. I timed it once, it stayed for about 2 hours. So try it at home. It's really fun to do at the kids' birthday parties. And it's magic. Well, it's not actually magic. It's principles of electricity. But when you see it, it looks like a magic. Another important concept is electrical ground. You've heard about it. If lightning hits a house that's not properly grounded, it can set house on fire. We don't want that. That's why we provide wire that is connecting, that provides a path to the ground. And why it works. First of all, Earth is huge, and it also everywhere, and it also generally moist, so it conducts well. That's important. The term ground is used to denote a path or destination of the excess charges, even if the dirt is not actually involved. Charging by contact. How we can charge object by contact? Pretty straightforward. I have a rod I rubbed it with the fur, or my cat, or your dog. It become negatively charged. I'll touch a copper coin. Here it is. Some electrons will leave and go to the coin. Then I would remove the rod, and it's still going to be negatively charged, but less. And a coin will be negatively charged, but less. So the charge on this rod Q is going to be split on Q1 and Q2. However, the sum, capital Q, is going to be stay equal Q1 plus Q2. Charging object by induction. Similar but different. Have a rod, rub it with a fur, have it electrically charged with negative charge. Bring it next to the coin, but do not touch it. Do not touch. What's happening? Coin becomes polarized. Polarizing the metal. That's what's happening. So one side of a coin has a positive charge, negative. Another side of the coin is going to be negatively charged. Then we would connect it coin to the ground, like in this picture. So those electrons are going to escape. Then we remove the ground, and the coin will stay positively charged. Just a quick summary for charging by induction. The electrons are able to use the wire to move even further from the charged rod. Some of the electrons will move off the original piece of a metal into electrical ground region. The final step is remove the grounding wire. The original piece of metal will be left with a net positive charge. And that's pretty much it. Thank you for listening. We'll have a quick review on Thursday, and see you soon.